now you should switch the microphone on.
Yeah.
Okay. So let me introduce the last speaker of this afternoon. He is Professor Pattinson from Imperial College in London, and he will speak about reasoning in non-wellfounded logics.
Yeah. So thanks for the introduction. Also thanks to the organizers. So I want to make the same disclaimer as the previous two speakers. So I'm speaking about work in progress. In my case, the work is in progress to an extent that I don't even have slides. And I want to tell you about a problem that I'm working on at the moment. And this is actually in the area of non-wellfounded modal logic, and the idea is to understand more about the proof theory, the semantics, the relationship to other formalisms. And so the aim of this talk is essentially to give you an idea of the problem sort of in a sort of comprehensive way. So, so it's only one problem, but maybe a bit more detail on that problem. So let's start with basic modal logic. So, as we all know, so we have a language which has formulae that are sort of either propositions, negated propositions. We allow ourselves conjunctions, disjunctions, and we have a box modality, and we have a diamond modality. So this is what we all know. Then,
Excuse me, are you sure that it's on? Because the
no, I thought I switched it on.
Okay.
No, I switched it off.
So it's no matter in which position it is, the light is not on. The battery is dead.
Oh, okay.
That's my bad.
Do you want me to continue or do you want me to pause?
Or start everything.
I can start again. So.
Even my wonderful introduction should be okay. Okay, well. So much for the technique.
Yeah.
He doesn't say anything.
No. But that's not so important.
Well, whoever watches it now on the internet, for example, this government, GCHQ, they can probably read, so why don't you just continue and pay attention to the...
Yep. Okay. So what I'm doing is just modal logic 101, but it's going to get a bit more interesting in 2 or 3 minutes. So just to remind you that so the language of basic modal logic is interpreted over Quirky models where we have a set of worlds, then we have a function or a relation that tells us about accessibility, and we have a valuation of propositional variables. So at every world it tells us which variables are true at that world, and formulae are evaluated at worlds. So a world W, with respect to model M, we know we have that box A holds if A is necessarily true. If A is true in all worlds related to W, which means for all possible relational successors of W, we have that A is true, MW satisfies diamond A if and only if there exists a relational successor. Okay, so that's all very nice, but from the perspective of computer science, if you will, not too useful. So basic model logic allows us to speak about a finite number of transition steps. So in order to speak about ongoing behavior, people usually look at fixed point logics, and the most general variant is the modal mu calculus, which adds to the syntax of basic modal logic. So there's many ways to do it. One possibility is to add fixed point variables, and then the ability to speak about least and greatest fixed points. So fixed point variables can't be negated, so everything is monotone. And if I have the modal mu calculus, I also interpret it over Kripke models, and the idea is that the truth set of a formula like this, so this is a mu formula, so mu stands for the least fixed point, so this is the least fixed point of the operation that takes a subset of worlds and gives us the interpretation of the formula where the variable x, let's write it that way, is evaluated to s. So there may be other fixed point variables, and I'm assuming an assignment that doesn't change. Similarly, if this were a nu, I would just compute the greatest fixed point here. So this is modal mu calculus 101. So continuing in the same way, let's look at some extremely simple examples. So let's look at just one fixed point. So let's consider the formula A, which is the least fixed point. So either P holds, or I have a successor where X is true. So given a model, we have that this formula holds if and only if we can find a successor so that the point of evaluation makes a number of transitions to this successor and P is true. So the way I want you to think about this, so if you think about a formula like this, so what you invariably do is to think that informally A, so what does A mean? So either P is true, or I have a successor where the formula A holds. So what does that mean? That means I have a successor where either P is true, or, so in this case, disjunction distributes over the diamond, or I have a successor that has a successor where P is true, etc., etc., etc. So I can think of this as essentially A as saying, well, either P is true, or I have successor where A holds. I can also think of this as a non-well-founded formula. So we have this junction, either P is true, or I have a successor where precisely this formula is true. So another example, equally simple, is the formula mu x, p and box x, and this formula means that, so wherever we go, p is true, and whenever we go somewhere, p must be true, and that recursively. So that means for all states that we can reach in a finite number of steps, we have that p is true at this state. So, and so applying sort of the same informal reasoning, I'm thinking of B as saying, well, P needs to be true. If I do one step, P needs to be true. If I do two steps, P needs to be true, etc. Or, again, as a non-well-founded formula, namely P and box B, or, if you like, a conjunction of P and then the same formula again. So that's all informal, that's the meaning of the quotes. But now I've done something slightly weird. So I've started with a least fixed point formula and then greatest fixed point formula, and I've rewritten them to infinite formulae, or non-well-founded formulae, just the way that I informally think about them. And there is no distinction between least and greatest fixed points anymore. And the question is, can we make this precise? Can we use, in a way, the idea sort of infinite formulae to maybe learn something about the mu calculus? Can we have sort of a notion of non-well-founded semantics and non-well-founded proofs? So what I want to do, so I'm going to present two results, but these are results that are easy to get, and then I will hint at things that I want to be working on. Okay, so let's take this idea of non-well-founded formulae seriously. So let's change the syntax again to non-well-founded modal logic. So there is no need for fixed point variables anymore. And so I don't want you to read this as a grammar in the inductive way. I want you to read this co-inductively, which I indicate by the infinity symbol. So formulae are now possibly non-well-founded trees constructed according to that grammar. And, of course, I would like to interpret this over Kripke models, ideally using these semantic clauses, where, of course, also the interpretation of fixed point formulae now goes away. Okay, so if you stare at this for a minute, you will see that, so for standard modal logic, we define the interpretation by induction of the structure of the formulae, as one standardly does. So if the formula is non-well-founded, this is something that we cannot do. So the first thing that we need to do is clarify on the semantics of non-well-founded formulae. Again, intuitively, we would like the semantics to satisfy these clauses. So the standard interpretation of modal logic. So let's think about the interpretation for a short while and then move on to proof calculi. So the idea is to change focus slightly. So let me rewrite some of the semantic clauses. So we have W satisfies P if P is in pi of W. We have W satisfies P bar if this is not the case. If W satisfies A, W satisfies B, we have W satisfies A and B. So let's write out the clause for the box operator. So W satisfies box A. Now I have a number of premises, namely W prime satisfies A, where W prime is the successor of W. And I'm not going to write out essentially all the rules, but I'm sure that everybody will see that I can write the interpretation of standard model logic in this way. But now what I've done is I've defined a monotone operator, and the semantics is just, in the classical well-founded case, is just a fixed point of this operator. So this defines, if you like, an interpretation operator. So what's the type of this operator? So it takes a relation between worlds and formulae that are founded at this world, and gives us another one. So if the premise is true, or all premises are true, then we get a new judgment in here. Okay, and what does it mean that we want these equivalences to hold? Well, that means that also in the non-well-founded case, we want the interpretation to be a fixed point of this operator, very precisely. So this is an operator on a complete lattice, so it's monotone, as can easily be seen. So we want a fixed point, now we have a choice. So we can take the least fixed point, which is the least fixed point of this interpretation operator, or we can take the greatest fixed point, which is the greatest fixed point of this operator. Now, if we come back to these two examples that I have unfortunately deleted, so there's okay, maybe one more sentence about this distinction. So we have an inductive semantics and a co-inductive semantics of non-well-founded formulae. So coming back to the examples, we have a formula A is P or diamond A. Then what you can see quite easily is that a world inductively satisfies A if and only if this world satisfies the least fixed point formula. And similarly, we had the formula B, which was P equals B, or a solution of this equation, if and only if this holds co-inductively. So, in other words, the distinction between least and greatest fixed points that we've lost by sort of following our intuition and rewriting these two these two fixed point formulae in terms of non-wellfounded formulae reappears in the choice of semantics that we choose to give them, whether we want inductive or co-inductive satisfiability. Okay, but what we have here are sort of two semantic relations. So the next thing that I want to do briefly is to think about a proof calculus and then speculate on further extensions that I'm currently working on. Oops. Okay, so the proof calculus I want to think about is a standard sequence calculus. So by sequence, I mean multi-sets of formulae. Just going to use a one-sided sequence calculus for convenience. I have some standard rules. So everything's a multi-set, so this is the axiom. If I have A and B, then I have their conjunction. So if I have A0, A1, up to AN, I have box, A0, diamond, A1, diamond AN. So this is proof theory for modal logics 101, if you like. Oops, that's not quite correct. Plus weakening. And it's well known that if I sort of add the disjunction rule, which I don't bother to write out, that this proof calculus is complete for the standard interpretation of modal logic. So, so in the same sense in which we've used the standard clauses for defining sort of a truth predicate, truth of a formula at a world, can we use essentially the standard proof calculus to tell us something about inductive or co-inductive truth? Okay, so again we're in a similar situation. We have rules, and these rules they define an operator on a complete lattice, if you like. So we take a bunch of provable sequence, which are the premises, and then add more provable sequence, which are the conclusions. So this may seem a bit formal. So again, what we want is that provability is somehow a fixed point of this operator. So if if formulae were well-founded, what you can see is that essentially every application of a proof rule peels off one operator. So co-induction would be essentially meaningless. But if formulae are non-well-founded, we have a notion of inductive probability that we can take as the least fixed point, and we have a notion of co-inductive probability, so we may consider the greatest fixed point of this operator. And it turns out that inductive and co-inductive proof is very nicely related to the notion of inductive and co-inductive probability. but this is essentially where sort of the simple relationships stop. So I have some results. Okay, let's call this, or maybe let's call it a lemma, namely that inductive derivability is sound with respect to inductive semantics. That's absolutely standard. So inductive derivability is a subset of inductive truth, where here I mean a relation on multi-sets of formulae, and it holds if for every Kripke model that you pick, at least one of the formulae in this multi-set is true. So how do you prove this? Well, you do an induction on the proof. So inductive provability is an inductive definition. It's at least fixed point, so we have a proof principle. Okay, so now let's do co-inductive completeness. That's also a lemma. It's extremely simple to establish, and the reason is that this is the greatest fixed point. So that means we have a proof principle. So the only thing that we need to show is that the set of all co-inductively valid sequence is co-closed under the definition of this operator. So that's just a few lines. So I'm hesitant to call it theorem, but it's slightly harder to do inductive completeness. So this is, something is inductively valid, then it's inductively provable. If something is co-inductively provable, then it's co-inductively valid. So these are the two directions for which we don't have proof principles, so we need to work. So here we're doing sort of a canonical model construction here. You can think about a notion of non-validity as being inductively defined as the least fixed point of the dual operator. Then we can do transfinite induction. And now I want to speak about questions. So this is the end of the result, or the results. So what we've seen is that we can understand various very simple fragments of the mu calculus in this way. So the language here is a lot richer. So everything that I can express in the mu calculus, if I just unwind it, is gives a regular tree. Here is sort of, I also have things that are non-regular. It just needs to be sort of non-well-founded. But not very much is expressible as it stands. So what's the general problem? The general problem is essentially how do we mix least and greatest fixed points. So what you can show is that either in the inductive or in the co-inductive reading, you get the fragment of the mu calculus, or you can encode the fragment of the mu calculus that either uses just least fixed points or just greatest fixed points. But it's hard to mix them. So there are sort of some ideas to do this semantically. The question is what happens to the proof calculus. The question is essentially what happens to the proof theory. So there are interesting questions, at least from my point of view. Do we have something like continuous cut elimination? And so the question that underlies this scheme is, can we understand the mu calculus in terms of mixed inductive and co-inductive proof? And I think I should stop here, and thank you all for your attention, and I hope that I haven't been overrunning too badly.
Thank you very much. Is there some questions, please? Joel, yes?
I have a question. In your non-well-founded, it seems like your non-well-founded syntax here is able to support things like the liar sentence and so on, and a sentence which is the conjunction of itself with itself and so on.
Yeah,
So
of course.
could you explain how the semantics of that work in your?
Yep.
So A equals A and A, it seems expressible and simple.
Yes.
So
you get lots
How does
of
its validity come out?
you get lots of weird formulae. Absolutely.
Is it different from B equals B or B?
Of course it is. But that depends on your chosen notion of interpretation. So we get formulae like A is box, so you have Y, and you just keep in boxes. We can have something like B and B. If you think about it, it's just an infinite descent into a conjunction. We can have the same for OR. So I think you were asking about...
Well, my question is about the semantics of these kinds of sentences.
Yeah. So I think you were specifically asking about this one.
Yeah.
So that depends on whether you view it inductively or you view it co-inductively. So intuitively, the co-inductive semantics of this formula allows us to procrastinate indefinitely. So that means, okay, so what do I need to do in order to satisfy B? Well, I need to satisfy both conjuncts, which are, again, B. How do I do that? Well, I need to satisfy both conjuncts. And what you can see here are the beginnings of an infinite proof tree. So what we prove is semantical judgment here. So if we think about the co-inductive interpretation, then this precisely says that infinite proof trees are fine. So as long as I can unravel the proof tree, and you can always essentially you can always provide sort of a rule that gives this, then the proof is accepted. So if I think about this,
so the liar would also come out to be valid then?
Pardon?
The liar, I mean the one that is the negation of itself. So A equals not A.
No negation, except negation.
Negation's only
Isn't it a key point of what you were doing that you're only working with negation normal form, certainly semantically, as far as I understood, because you're relying on monotonicity.
I'm relying on monotonicity, yes.
So you've got negation normal form, but if you never hit any propositional atoms, then.
Oh, so you can only negate propositions. I see. Okay. So there is no liar here.
Okay. So what you can do is So, by the way, just to conclude this, inductively, this would not be the case, because inductively we're saying that we want a finite derivation tree, and essentially, whatever we do, we will never reach an axiom. So you can also think of it as very simple two-player games. So here, both for the interpretation and for the proofs. So for the interpretation, essentially we have two players. I like to call them Eloise and Abelard. So Eloise wants to demonstrate that this judgment is true, so she picks a rule, and Abelard may challenge her for every premise of the rule, so where she again has to pick a rule. And there's a difference in the winning conditions for the inductive and the co-inductive interpretation, namely that inductively Abelard wins infinite place and co-inductively Eloise wins infinite place. So for purposes of negation, you've correctly observed that I was cheating, and you can define a formal negation in the sense of saying, well, what is the negation of A and B? This is the negation of A, or the negation of B. The negation of box A is diamond not A, etc., etc. So this is a perfectly well-defined operation, so you can think of it as guarded, and it just percolates down infinite path trees, if you will, of formulae. And then what you can show is the following. So if W doesn't inductively satisfies A, this happens if and only if W co-inductively satisfies the formal negation of A, and the other way around. Which means that negation is not expressible in the logic unless I have both fixed points. So one way to address negation is to work with two-sided sequence in a standard way. So let's now take two multi-sets of formulae where we think of these as being positive, these as being negative, and then to interpret negation you just shuffle formulae from one side of the sequel arrow to the other. What is, at least to me at this moment, not so clear is how the proof theory of two-sided sequence calculus here really looks like, or not so much the proof theory, more the questions of completeness. So, but if you do something like this, so this is in relation to one of the things that I mentioned, namely cut elimination. So now we have a two-sided sequence calculus. We can think about the soundness of the cut rule. We can think about cut elimination. So now a proof with or without cuts is sort of an infinite object. So one question is whether cut elimination is a continuous procedure or not with respect to a suitable metric that captures the syntactic difference between formulae.
Well, I'm not sure if they are actually not closing the whole building at 6. I would suggest that maybe we can take the discussion to the main building. Or isn't that the case, that this is being somehow automatically locks at 6 p.m. or?
I think we can always get out.
Well, if you think so, well, please go ahead.
Shall I?
Yeah, please do, yes.
Well, so one question was, so I recall that James Brotherton was doing some work on non-wellfounded proofs in a kind of time theory setting. Is there any connection?
Yes, of course there is. So for the So that is sort of, in fact, part of the technical motivation. We can think of sort of say a sequence calculi for something like the mu calculus, where we have sort of both least and greatest fixed points in terms of being given by a sequent system, but whenever you sort of start reading one of these papers, what you find is a coherence condition on non-well-founded proofs. That says, okay, a proof is basically, well, we can think of it as sort of an infinite, sort of in the case of regular formulae, regular tree, but we're not going to accept any proof. So we're not going to accept that chasing through the proof, a least fixed point formula is unfolded infinitely often. And that is a notion of a trace through a proof that essentially you find in all treatments of completeness for the modal mu calculus. And so what you need to do is you need to do a lot of bookkeeping. So essentially you say that, okay, so the trace of a formula like this, oops, no, that's precisely wrong, so this is B, or if we go this way, it will be A, and the formula in gamma will just be repeated. So this is a notion of trace through an infinite proof. What you require is that essentially on no trace, so if you have a proof, there may not be a trace where sort of a mu formula is unfolded infinitely often, which is technically, of course, correct. The question that I'm asking is whether it's not more natural to think about proofs for sort of formulae involving greatest fixed points as being co-inductive, and then possibly also achieving a more natural treatment of sort of a purely, so that the vision is to have sort of a purely inductive, co-inductive proof theory. Not something where we have a notion of proof and then we have sort of a soundness predicate on proofs.
Okay, everybody satisfied? More questions? Well, if not, let's end this.